Well, welcome to the lecture 6.4 covering graphs of logarithmic functions. Now, in our previous 3 sections, we have covered exponential functions and the graphs of exponential functions. In 6.3, we figured out that the inverse function to exponential functions is a logarithmic function. And so now we're going to take a look at what those logarithmic functions appear like on a graph. Okay, so how do logarithmic functions give us insight into situations? So this is a little connection as to how this can be useful information for you. And it says because every logarithmic function is the inverse of an exponential function, we can think of every output on the logarithmic graph as the input for the corresponding inverse exponential equation. So this is a characteristic of the inverse functions that we know very well by now, in that the input and the output are exactly flip-flopped in inverse functions. So what we can do is when we invert these functions, we can basically find and give the cause for some sort of effect. So it's nice to see this in a concrete example here. So suppose we invest $2,500 in an account that offers an annual interest rate of 5%. Compounded continuously. So I'll just remind you that this equation right here is modeled from the PERT formula, A equals P times E raised to the RT, and that is used for continuously compounded interest. So using that information, we would have this function specifically, account value is equal to 2,500. That's our principal deposit, or let's see, we invest. So yeah, that's a deposit, times E, and that's gotten from 1 plus 1 over n to the n as n moves into infinity, raised to the rate times time, and in this case we know the rate, and that particular rate is 5%, which is written as 0.05 as a decimal. So that's where that equation came from, and you should already be familiar with that from 6.1. So what if we wanted to know the year for any particular balance? So say I've put this money into the account and I want to know, okay, how long is it going to take me to reach a balance in my account of $10,000? That $10,000 would be input in for my account balance, and I would need to solve for T, time in years since the account was first invested in. So knowing how to work with logarithmic functions graphically, we can kind of backtrack and solve for the other variable, especially when that variable is sitting in the exponent, which before we discovered logarithms, we would not know how to solve for except by graphing both sides of an equation and seeing where those equations intersect. But we saw in 6.3 that that's not necessarily the most efficient and accurate or precise way of solving for that variable. Okay, so let's talk a little bit about the domain of logarithmic functions. So recall that an exponential function is defined as y equals b to the x power for any real number x. Your base b has got to be a positive value and it cannot be 1. we know that the domain of any exponential function is negative infinity to positive infinity. And the range, when we haven't translated vertically, we know that that range is going to be 0 to positive infinity. So when we think about characteristics of inverses, and we know that the logarithmic function is the inverse function for an exponential function, notice our domain and our range are exactly flip-flopped. I now have a domain from 0 through positive infinity, because think about plugging into this function here for x. Remember, I can't take the log of a negative value because there's no way to raise a positive value to any exponent that will ever yield a negative value. So now my domain is restricted to only positive values, and my range has now become the domain from my exponential function, which is negative infinity to positive infinity. So all outputs are possible here. All right, so transformations of the parent function y equals log base b to the x behave similarly to those of other functions. Thank goodness. We have now addressed shifting, stretching, compressing, and reflecting in about 5 or 6 different sections so far. And so this should not be a shock to you. This should be very easy for you from here on out. So hopefully that's exactly what it is. So let's go back to the domain. Now, how do we identify the domain of a logarithmic function? Well, we have to know about the left and right shifting. With the exponential function, we were worried about vertical shifting. That's what was going to change our domain, which also changed our asymptote. Well, since the logarithmic function is the inverse of the exponential, now we have to worry about left and right shift of these functions. So if we go here, we can see a piece of a logarithmic function there, and our asymptotes for logarithmic functions are vertical. So if we shift left and right, that's going to move our asymptote, hence restricting our domain. So when these logarithmic functions have not been shifted at all, we have x equals 0 as our vertical asymptote, making our domain 0 to positive infinity. So to figure out the domain, if something has been shifted in the horizontal direction, we just need to make sure that whatever's on the inside, whatever we're taking the log of, ends up being greater than 0. Because once again, we cannot take the logarithm of a negative number. Well, we can, but we don't get a real number answer there. So we need to figure out, well, when will x plus 3 be greater than 0? So this is a simple linear inequality to solve. We subtract 3 from both sides and get x is greater than negative 3. So the domain for this function is anything strictly greater than 3. So we can either write it in inequality form, or I can write it in interval notation. So my domain of f in this case goes from negative 3 non-inclusive through positive infinity. Same thing here. It does not matter if you've shifted vertically with these, because our range is negative infinity to positive infinity. It's the horizontal shift that we have to worry about. So we need to find out here, when will x minus 2 be greater than 0? Add 2. That will happen when x is greater than 2, so the domain for my function f goes from 2 through positive infinity. Okay, so let's take a look at graphing a logarithmic function here. And we're going to graph it right next to its partner inverse exponential function. Okay, so we begin with the parent function y equals log base b of x, because every logarithmic function in this form is the inverse of an exponential function with the form y equals b to the x. Their graphs will be reflections of each other across the line y equals x. So because I know I'm about to graph inverses, I can go ahead and mark my line of reflection y equals x. All right, and for the sake of time, I went ahead and included the x and f of x tables here. So one thing I would like to point out is if I input -3 into my exponential function, I get out 1/8. But I have to flip-flop that for my logarithmic. So that would say I would input 1/8 and get out -3. So actually, let me change the color here so I can put these onto the graph. So these are just the points laid out for us, so we don't have to go through the process of evaluating all those to put them onto the graph, just so we can get a good picture of what it looks like. So I'll go ahead and graph my exponential function 2 to the x. Notice that I have to have the same base if I'm talking about inverse functions. So my exponential function is base 2 raised to the x power, whereas my logarithmic function is log base 2 of x. Okay, so -3, 1, 2, 3, 1/8. -2, 1/4. -1, 1/2. 0, 1. 1, 2. Oops, I went up one too many. 1, 2. There we go. 2, 4. Asymptote is the x-axis here. This is my exponential, and it's going to go off into positive infinity there. And now let's take a look at the corresponding inverse logarithmic function. Positive 1/8, -3. Positive 1/4, -2. Positive 1/2, -1. 1, 0. 2, 1. 4, 2. Okay, so now the y-axis is a vertical asymptote. And you can see that my functions, sure enough, reflect across the identity line y equals x. Okay, so just some general notes about the parent function log base b of x. As we already know, b has got to be greater than 0 and cannot be 1. It is a one-to-one function, which means that it has an inverse, and that inverse is also a function, and we know that inverse function to be an exponential function, has a vertical asymptote, which we just saw at x equals 0. Domain is 0 to positive infinity because of that asymptote. Remember, we cannot take the log of a negative value. Range is negative infinity to positive infinity. Okay, so our exponential functions had that key point of 0, 1. Our logarithmic functions will have a key point of 1, 0. And other key point, this is our base b, and our output is 1 there. Okay, y-intercept, there are no y-intercepts if I have not translated horizontally in the negative direction. It's increasing, and it's increasing if our base is greater than 1, and it's decreasing if our base is between 0 and 1. So here we have an example of our base being greater than 1, and here we have an example of our base being between 0 and 1, so some fraction between 0 and 1. Okay, let's put one of these onto the graph. So we'll just create an f of x table. And I have not translated, so I know that this is going to go through the point 1, 0. And I know I can't plug any negative values in. So I'm going to choose to plug in 1/5 for x, and I'll just show you what that looks like. So if I'm going to evaluate f of 1/5, I have log base 5 of 1/5, which is the same thing as log base 5. I'm going to bring that 5 up into the numerator, so that's 5 to the negative first power. So what this is asking me is, what can I raise 5 to raise 5 to the negative first power? So that is -1. Now I need to go greater than 1. So I'm going to choose a very nice, neat number of 5, because now f of 5 is saying, what is log base 5 of 5? In other words, what can I raise 5 to make 5? And that has to be 1. Okay, so everything else that would be nice and neat for us to graph is off of our graph. I would need to be showing 25 to get my next integer as an output value. So I'm going to go with this. So I already know that my vertical asymptote, because I have not shifted horizontally, is the y-axis, which is x equals 0. So we've already answered this question right here. What is the vertical asymptote? Okay, I'm going to go ahead and put this onto the graph. 1/5 -1 is about right here. And I've got 1, 0 and 5, 1. So this thing comes up from -infinity, getting closer and closer to that vertical asymptote, and then kind of, it doesn't level off, but it's increasing at a very low rate. So the domain of this function is 0 through positive infinity, and my range is -infinity to positive infinity. Okay, so now we're going to start with our transformations. And horizontal shifting, we know, happens on the variable. It happens on the inside of the function. And don't forget inside inverse. So when you see x plus a value, it's actually going to shift to the left or to the negative side that many units. And when you see x minus c, it's actually going to shift right c units. And that happens on the input. So any horizontal shifting, when we show it in our tables, is going to happen on the x value when we shift from our parent form of the function. Okay, so let's start out with our parent x f of x table. So our parent function in this case would be g of x equals log base 3 of x. Okay? So x and g of x, and we'll shift from there. Okay, so I'm going to do 1/3 because 3 raised to the negative first power is 1/3. I'm going to do 1. 3 raised to the 0 power is 1. And I'll do 3. 3 raised to the first is 3. And I'll do 9 since it's on our graph. 3 raised to the second power is 9. And then I don't have any other integers on my graph that I have here. So we'll stop there. And now we have, and let me go ahead and put that onto the graph so we can see how we shift from this parent function. So 1/3, -1, about right here, 1, 0, 3, 1, and 9, 2. This comes up from negative infinity. All right, so what we should expect with our new function, our translated function, is a shift 2 to the right. Remember, inside inverse. So f of x equals log base 3 of x minus 2. This means we are going to add 2 to each of our input values. So I start with my regular input from my parent, 1/3, 1, 3, and 9. And then I have my translation of 2. And that gives me my new x values of 2 and 1/3, 3, 5, and 11, and my y values don't change. I have done no translating in the vertical direction. So 2 and 1/3, -1 is about right here. 3, 0, 5, 1, 11, 2. So my vertical asymptote for my transformed function is 2. So just so you know, x minus 2 has to be greater than 0, so x has to be greater than 2. So I've got that vertical asymptote at x equals 2. And now I'm just going to finish graphing my logarithmic. Okay, so domain of f goes from +2 through +infinity, and the range of any logarithmic function is -infinity to +infinity. Okay, vertical shifting. Now we don't have to worry about our asymptote shifting when all that's happened is a vertical shift, because our asymptote is vertical. So it's the left and right movement that's going to change our asymptote, not the up and down movement. And up and down movement or vertical shifting happens on the outside of the function. So if I'm adding some value, I shift up that many units. And if I am subtracting some value, I shift down that many units. Okay, so we'll start again with our parent function. And in this case, our parent function is log base 2 of x. Okay, so 2 raised to the negative first power is 1/2. 2 raised to the 0 power is 1. 2 raised to the first power is 2. 2 squared is 4. We can fit 2 cubed on here. That's 8. Oh, we can even fit 2 to the 4th on here. That's 16. That shows up on our graph. Okay, so let me go ahead and put this parent onto the graph. 1/2 negative 1, about right here. 1, 0, 2, 1, 4, 2, 8, 3, 16, 4. So here's our parent. And then from our parent, to get our new function, we're going to shift everything up to. That happens to your y value, so that's the only thing that changes. So f of x is equal to log base 2 of x plus 2 outside of those parentheses. So it's outside the logarithmic function. So my x values are going to remain, and I will add 2 to all of my, oops, that's f of x values. So I have 1/2, 1, 2, 4, 8, and 16. And then I have negative 1. This is what I'm starting with. 2, 3, 4. And I have a vertical translation of up to, up to, up to, up to, up to, and up to. And that ends me at 1, 2, 3, 4, 5, 6. Okay, so I have 1/2, 1. 1, 2, 2, 3, 4, 4, 4, 4, 8, that's 5. Okay. 8, 5, and 16, 6. So I still have that vertical asymptote at the y-axis, so x equals 0. But you can see this whole thing has been shifted up to. Okay, so vertical asymptote at x equals 0. My domain has not changed from the parent. It's 0 through positive infinity. And my range is always negative infinity to positive infinity with logarithmic functions. Okay, stretching and compressing. So we're only going to talk about vertical stretching and compressing. And when the factor, so this happens on the outside of the function multiplied as a factor on the entire function to affect the y values, which is the vertical direction on our graph. So what we see here is that if A is greater than 1, it's going to be a vertical stretch. And if A is between 0 and 1, then it's going to be a vertical compress. Okay, so we actually have more than one thing happening here. We have a horizontal shift, we have a vertical shift, and we have a vertical stretch. And I don't think I've got enough showing on this graph. We'll see when we get into it. Okay. So this is just the common log as our parent function. G of x equals the log of x. And don't forget, that's understood to be log base 10. So my parent if I raise 10 to the negative first power, I get 1/10. If I raise 10 to the 0 power, I get 1. If I raise 10 to the first power, I get 10. And that's all I'm going to be able to show on this graph. Okay, so 1/10, negative 1, 1, 0, 10, 1. So this is my parent. Very flat looking. All right. So my transformed function, f of x equal to 3 times the log of x minus 2 plus 1. Okay, so the first thing that we want to do in transforming is to add 2 to each input value, and then I will, on my outputs, multiply by 3. Oops, let me keep my colors consistent. I will multiply by 3. And then add 1 to each of my outputs to get to my transformed function. So, start with my table here. F of x. Okay, so 1, 2, 3. I start with 1/10, 1 and 10, and here I start with negative 1, 0, and 1. All right, so for my input values, I am adding 2 to each. And that leaves me with input values of 2 and 1/10, 3 and 12. And then with my outputs, I'm going to multiply by 3. And then I need to add 1. So I get new output values up. Okay, negative 3 times 1 is negative 3 plus 1 is negative 2. Negative 3 times 0 is 0 plus 1 is 1. Negative 3 times 1 is 3 plus 1 is 4. Okay, so I have the points 2 and 1/10, negative 2, 3, 1, and 12, 4. So it should look like this function has been stretched in the vertical direction. It's been shifted to the right 2 and up 1. All right, 2 1/10, negative 2. 2 1/10, negative 2 is about right here. 3, 1. 12, 4. Okay. So for my domain, x minus 2 has got to be greater than 0, so x has got to be greater than 2. So I have a vertical asymptote at x equals 2, which means my domain will go from 2 through positive infinity, and my range, as usual, is negative infinity to positive infinity. Okay, reflections. So if you multiply by a negative on the outside of the function, that is a reflection in the vertical direction. So that is going to reflect over the x-axis. If you multiply by a negative on the inside of the function, that is a reflection over the y-axis. But, let me point this out, when you reflect over the x-axis, that is happening to the y values. And when you reflect over the y-axis, that is occurring on the x values. All right. Okay, so notice, I've had reflections over the x and the y. So actually, I am certain that this graph is not going to suit our needs. Let me go to Desmos and grab a new blank graph. I'm going to make this smaller so that I make sure I can fit everything I need to on here. All right, I'm taking a screenshot. Give me 2 seconds. All right. Let me paste it here for us. Oh, that's big. Got smaller so it fits. There we go. Okay. So this is a common log, because I do not have a log base written, so I assume that it is log base 10. So my parent is just the log of x, which we've already looked at this x, y table. Okay, so when I raise 10 to the negative first power, I get negative 1/10. I'm sorry, not negative 1/10. I get positive 1/10. When I raise 10 to the 0 power, I get 1. When I raise 10 to the first, I get 10, and I can't fit 10 squared on here. That's 100. Okay, so I have reflection on my input variable, and I have reflection on my output variable. So basically, I'm just going to multiply both my x's and my y's by negative 1. So f of x equals negative log of negative x. And I start with my parent coordinates. So I'll start with 1/10, 1, and 10. And I'll start with -1, 0, and 1. Okay, so on my x values, I multiply each of those by -1. And I end up with -1/10, -1, -10. And then my y values also get multiplied by -1. And I end up there with +1, 0, and -1. All right, so we should expect our function to end up in the, okay, so let's see. If our parent looks something like this, if I reflect over the x-axis, it's going to look like this. Oops. Hang on. Let me try that again. If I reflect over the x-axis, it's going to look like that. And then if I reflect over the y-axis, from my reflection over the x-axis, it's going to look like this. So I should expect my function to live in the second and third quadrant when I put it on the graph. Okay, so that's what I'm going to do, is put it on the graph, and we'll see what happens. So I've got the points -1/10, 1, -1, 0, and -10, -1. All right, so -1/10, +1 is about right here. -1, 0 here. So these are counting by 2, so I'm halfway between those. And -10, -1 here. So sure enough, my function lives in quadrants 2 and 3. All right, so my domain, -x has got to be greater than 0. Divide both sides by -1. Whenever you're working with an inequality and you divide through by a negative, you flip the sign. So x has got to be less than 0. And notice my entire graph is graphed to the left-hand side of the y-axis. So my domain here is from -infinity up to, but not including 0, and then my range is the same. Range is always -infinity to +infinity. Okay, and this last concept, it's the same concept we've done in the past, and that's graphing two sides of an equation using our graphing calculators and then finding where they intersect to solve for x. So for this first one, I will go into my calculator and put y1 is equal to 4 times the ln of x plus 1, and my y2 will be -2 ln of x minus 1. Okay, so let me do that real quick. Y equals, okay, 4 times the ln of x, end parenthesis, plus 1, and my y2 is -2 times the ln of x minus 1, end parenthesis. And then I just hit graph, and my window is still set from an old graph. Oh, but actually I can see I'm gonna zoom in a little bit more so I can get a better picture. One quick way to find interesting parts of your graph is go to your zoom function and arrow all the way down to zoom fit. Okay, now I've got a really nice picture of these two graphs. One is increasing and one is decreasing. And let me see if Desmos will, I don't know if Desmos has the ability to do logarithms. Let's go check it out so we can take a look together. Let me make sure I'm on my calculator. Yeah. Okay. I'm going to make this a little smaller. And I need to show my input. Okay, so we had, shoot, I didn't write down that function. Let me pull it up in my notes here. Give me 2 seconds. Open 6.4. Okay, let me get this equation. Or function rather. Okay, 4 times the ln of x plus 1. Let's see if it'll graph this. 4 times the ln of x plus 1. Okay, nice. We've got that one. Now let's see if we can put the other side on there. Negative 2 ln of x minus 1. Okay, so negative 2 ln of x minus 1. Nice. Okay, so they don't have a calculate, but we can probably get pretty close. So this is looking like it's about 1.32, 2.279. I'm going to calculate it on my TI calculator here, so we can get an exact calculation. And to do that, you do second and trace, which is your calculate menu, arrow down to 5, which is intersect. Put your cursor on one of your functions and hit enter. Put your cursor on the other function and hit enter. And then it says guess, but just hit enter. Okay, my calculator, my TI is saying that intersection point, and I'm just going to highlight it again for us to look at, is 1.3385, so that's 1.34, very good. And y is 2.1662, we're a little off there. Okay, so 1.33, 2.217, so that's it. 1.33, 2.217. So what we're interested in is the x value, because that solves our equation. So in this case, to make this true, it says round to the nearest thousandth. X is equal to 1.339. Okay, same thing with the next one. I'm not going to show you on Desmos because we've already seen that and I don't want to waste your time. So 5 times the log of, I'm just putting this into my TI calculator, x plus 2. And my y2 is 4 minus the log of x. I'm going to graph that. Okay, I'm already seeing a good picture. I'm ready to calculate the intersection. So second and trace, arrow down to intersect, hit enter, first curve, enter. Move to my second curve, enter, guess, I don't care, I'm just going to hit enter, and I find here that X is approximately 3.049. That's all I have for you on graphing logarithms. I hope this is helpful.